Hi everyone, Dr. Anna here. We are continuing the origin and environment of sedimentary rocks module, and this is going to be segment 5. We stopped at the glacier deposit environment, and now we are at the desert and arid basins. The first very important thing we know about these environments that we have no chemical weathering, it's only physical weathering. Therefore, there is no soil in these environments. In the spring, there is a couple of rains, and that rain is evaporating as soon as the sun hits it. And therefore, we see some carbonate precipitation in the lake environment, like on the bottom of the valley. Usually, these are grabens. We will see these very characteristically along divergent plate boundaries when it's on continent. We have not only carbonate, but also evaporates, gypsum, anhydrite rock salt, which is, remember, the halite. And from the mountains, when there is rain, it is very energetic. It has a lot of power and it brings down a lot of sediment from the mountains and it will settle down right at the alluvial fan. I hope you remember from physical geology. So these are very characteristic sediment in the area. So basically, the alluvial fans are not going to be anything but unsorted polymeric breccia and conglomerate. It's a little bit similar to the tillite, but when you see the anhydrite gypsum and carbonate precipitation close by it, you know we are not in a glacier. The other very characteristic feature in these areas are the mud cracks. You know, anytime you have rain and then it dries and then rain and it dries, you're going to have a lot of mud cracks. Very interesting that sometimes the mud cracks actually present in the evaporate. They have interesting names in that valley, like the Devil's Golf Course and that kind of name. So that just means that these are areas where nobody would want to play golf. That's why they say the Devil's Golf Course. Then the sand dunes are very, very characteristic. Why? Because it's dry. There is a lot of physical weathering, so there will be quartz sand, a lot of it, and then the wind will blow it because there is a lot of wind in the desert areas. So you will see amazing cross bedding, like on this picture right here, because the wind direction is changing a little bit and the amount of energy is changing. Each layer is a little bit different, which is very characteristic for wind carried sediment. If there was some changes in the climate and it becomes more humid, then the dunes will become stable and there will be soil formation on it possible. Okay, now we are at the river system as a depositional environment. We're going to start with the alluvial fan we just talked about, the braided stream, meandering stream, and the delta. Remember, we talked about this in physical geology, so I'm just going to touch it. So let's start with the alluvial fan. The sediments of alluvial fans usually form down in the bottom of the valley because the sediment is coming from the very steep mountains. During the storms, the sediment comes down like crazy, absolutely unsorted. Every kind of grain size is going to be present. It has a lot of energy because of the steep slope, but when it gets down to the bottom of the valley, speed suddenly goes down to almost zero. The river must put down the sediment and it's going to make a fun shape, just like that. And then low rivulets will be between these. So it looks like a fan, and that's why we call them alluvial fan. Steep mountain, fast flowing water. There's a lot of rain, lots of energy. As soon as it hits the bottom of the valley, speed goes down, so it cannot carry the sediment anymore, and it has to be put down, and it have to split into low rivulets because the sediment always blocks the next coming sediment, so it has to split into 100 low rivulets. So that's the typical alluvial fan. The next slide, I have a picture of the alluvial fan sediment, so you can see through time as the energy of the water flow is changing. Sometimes it's really, really high energy, big, big storm. Sometimes it's not that high energy, and then you got finer grained areas. Like there is one here, like some here. And there are times when it's really, really big grain. So that means it's more powerful flow. Now we are at the braided stream. Usually the braided stream will form right below the alluvial fan area. So you are a little bit lower part of the mountain. And you can see that because of the presence of a lot of sediment, the river will break up into low rivulets and sediment bars. Therefore, it has a complex network of channels and islands. The bars between the channels are filled up by coarse-grained, hardly rounded, poorly sorted sediment. It's more like breccia and conglomerate. In the channel, the sediment is usually cross-bedded, like a lot of the channel sediment is characteristic with being cross-bedded. Now we are at the meandering stream. This is the curving river with many noticeable bends and turns. These channels are seen in areas where the topography is gentle or nearly flat, such as plains and valley bottoms. So on this picture, you can see a really typical meandering stream with the Oxbow Lake, as you can see on this slide. So as the river meandering, you see it hits the side of the bank and it's going to be eroding on the other side because it's faster on this side. But on this side, it's slower, so therefore it deposits. So erosion, and here it's deposition. I just said that. So as this erosion going on this side, the river will move this way. And right here, this is the erosion right here, and that's the deposition, the point bar. So therefore here the whole thing is going, the whole river is going to the right. So the bands are going to be steeper and steeper. And then after a while, it will cut off and make the Oxbow Lake, just like this one. So you can see that the whole system is moving back and forth from the floodplain. As we learned in physical geology, it's very interesting because these deposits are mostly floodplain deposits and they are full of organic materials, so providing excellent soil for growing vegetables and other plants. You fly over the whole system and you can really see the development and that the stream is moving back and forth on this floodplain. You can see like old oxbow lakes, and there is another one forming right here. That's going to be an oxbow lake. There is some old oxbow lakes right here. So you can see the best way to see meandering streams is to fly over them. And now we are at the delta, and delta forms when the stream enters the ocean. Around the delta, sediment becomes finer grained, lots of silt and clay accumulates because it's slowing down again because the delta is coming. So here is Gulf of Mexico, that's the Mississippi Delta. The river is trying to come into the ocean, but the ocean is going back and forth, either because of the tide or because of the waves. So therefore, it basically stops the sediment movement and the speed really goes down to almost zero. Therefore, the channels again have to split and they make a typical delta shape. And all the sediment is being put down. And because it's basically stopped, the clay sized sediment can deposit as well. So in the channels, you're going to have fine grained quartz sandstone, and the sediments in the delta are frequently influenced by marine processes such as waves and tide. As I said, that's what stops the flow. Okay, so we have to learn more about the delta because it's a very important oil reservoir, usually, especially during the Mesozoic. We're going to learn about it pretty soon. There is a lot of deltaic sediment, which are excellent oil reservoirs, as I said. So we have to learn about the delta progradation. So the delta has some characteristic parts. The pro-delta, which is the area before the delta. We have the delta front, along which the sediment is settling down. And we have the delta plain, which is on the top. That's how the river is flowing, coming into the ocean and settles down, okay? Because of the sediment input all the time from the river, the delta is building out toward the ocean, you see? And that building out is what we call progradation. And as I said, this is important because they are very good closed reservoirs for oil because the river sediment is clastic, it has pore space, but next to the rivers, usually it's clay or very fine grained silt. So they are going to be closed reservoirs for oils. And we're going to learn more details about the deltaic sequences. And now we are at the transitional environments. The transitional zone is the zone between marine and continental environments, which includes the delta we just talked about, the beach, the tidal flats, and the coastal swamps. Okay, so let's start it. We just talked about the delta, so we're not going to talk about it again. We're gonna talk about the beach. I mean, you all know about beach, and you all love the beach, most of you, anyways. So the beach is shoreline accumulation of sand or gravel transported by the longshore current. When you have extra sediment, it will settle down right there and becomes wide or narrow beach, depending on how much extra sediment is in the longshore current. Usually mature sediment. It's usually well sorted, well rounded grains, usually quartz. That's why I say it's mature. Remember, mature sediment is when it's quartz sandstone. Sometimes, if the beach is high energy, it will have large grain size, such as pebbles. I haven't really seen any pebble beach on the East Coast except in Maine. Also, the sand on the beach can be carried by wind and that will form sand dunes. And in the dunes, because it's blown by the wind, there will be cross bedding. It's very characteristic. This just shows you a typical dune field, which has a lot of. This is the thing, the beach are never stable. It's always changing depending on the size of the storms, if there is any storm at all, and the wind direction, all of those factors are going to influence the beach. The second transitional element is the environment, is the tidal flat. The tidal flat is the area which is completely absolutely influenced by the tide. We have the supratidal zone, which is usually above the tide line, but sometimes during storms, it actually gets underwater. Then you have the intertidal flat. The intertidal flat is the area which is underwater during high tide and no water during low tide. And then you have the subtidal, which is always underwater. Many times the beach is surrounded by coastal swamps, which is basically standing water with trees. And this is the main area for coal formation. We could have coal in the mid latitude areas. This is the mid latitude. We usually have pine trees where you know that it's a coastal swamp, that the water is black. The trees have very wide trunks and they will have breathing tubes coming out of the water. The water is black from organic material. And then you have the subtropical, tropical with the mangrove. So this is mangrove here. So the mangrove comes around in Florida. In Georgia, where I live, a lot of the times we don't have mangrove. We still have pine forest swamp with alligators in it. Have I told you? That's kind of a scary thing. Now we are in the marine environment, and here we have to talk about the continental shelf, which is the flooded edge of the continent, organic reefs at the shelf edge, continental slope, the rise, the abyssal plain, and the trench. So continental shelf, this is an amazing picture of the continental shelf. You can see that this here is the shelf edge. Most of the time, the edge to the deep water, it's really short. If you go to the Caribbean, you can see the beautiful turquoise blue water, and then boom, it's much deeper blue, which means it's really deep water. Here, the sedimentation is controlled by tides, waves, and currents. And of course, it's also controlled by the latitude, if it's in the tropics or in the mid latitude or the polar areas. So here, if you have tropical climate, you're going to have mostly carbonate sediment. When you have the temperate shelves, they're usually dominated by quartz. Quartz can come through the rivers, or it can also come by the longshore currents from more northern areas. The polar areas are dominated by glacial sediments like till and ice rafted big pieces of rocks. And of course, it's full of sand and could be even silt. This is the shelf edge, where in the tropical areas you got the organic reefs, and the reefs are wave resistant, mound like structures, and they are made up of carbonate skeletons of organisms such as corals. Corals always live in symbiosis with algae, so they have to be in the photic zone because the algae is photosynthesizing. They live in, as I said, always live in the tropic photic zone. Here I have a nice movie about the coral reefs.
In this lesson, we're going to look at the different types of coral reefs. The first one we'll take a look at are fringing reefs. The fringing reefs grow near the coastline, around small islands, and continental land masses, wherever there is a hard surface. They are separated from the shore by a narrow, shallow lagoon. And fringing reefs are the most common type of reef that you'll encounter. Another type of coral reef formation is the barrier reef. The barrier reef can be found parallel to the coastline, but unlike the fringing reefs, they are separated from the land by a deeper and wider lagoon. Sometimes at the shallowest point, the barrier reefs can reach the surface of the water, forming a barrier to navigation so that boats aren't able to pass. The world's largest barrier reef is the Great Barrier Reef of Australia, which runs about 21 kilometers along the northeast coast of Australia to New Guinea. A third type of coral reef are atolls, and they are usually found on top of volcanic islands. Atolls have a centrally located lagoon, and they can vary in size from 1 kilometer in diameter to over 130 kilometers long. There are more than 300 atolls found in the Indian and Pacific Ocean. The water in the lagoon of an atoll is connected to the open sea by gaps found in the coral reef. There are also patch reefs. These can occur within the lagoons of the atolls and the barrier reefs. Where you find patch reefs, they are usually numerous in number.
So this here is a very typical fringing reef. You can see the turquoise color, which is the very shallow reef. There is a little bit of out here too. And you can see behind the reef, the ocean color is really dark blue, which shows that it's very deep water, while the turquoise always means very shallow water. Fringing reef just means, remember, it is attached to the land. Next one is the barrier reef here. See the reef front right here, the really dark blue in front of it. That just means very deep ocean. And behind the reef is the very, very light blue turquoise color, which shows that it's a very, very shallow, and the land is now pretty close to it. And these are typical atolls. You could have called it without me. Remember, the island is now below the surface because the sea level rose. So therefore the island got submerged, but the corals can keep up with the sea level rise. They can grow 6 meters per 1,000 years. So they can keep up with the fastest sea level rise. Now that you have seen all the different type of coral reefs, we're gonna continue with a movie about the structure of the coral reef.
We're now going to take a look at the reef structure. Although there are different types of coral reefs, they do have some things in common, which is the structure of the reef. Here we have a diagram showing a typical reef structure. To the left, we have the sea, and to the right, we have the beach. Rising up from the lower depths of the ocean to water level, right near the surface of the water, is an area called the reef front. The slope of the reef front can be either steep or it can be gentle. This is a low-stress area, which means there's not a lot of wave action and it's relatively calm. Corals like the brain coral and the pillar coral usually settle in this area. As we move further up, we encounter the reef crest, which can sometimes protrude out of the water. Now this area has very high wave stress, and so the corals that grow here are usually branching corals like the Elkhorn coral, which can diffuse some of that strong wave action. As we move further toward the beach area, we also encounter an area called the reef flat. The reef flat is also called the back reef, and it's found behind the reef crest. It can be short or several hundred meters long. The water can be shallow or it can be several meters deep. The bottom of the flat usually consists of rock, sand, and coral rubble, or some combination of these. You'll also find seagrasses growing there in the reef flat area. The reef flat of atolls and barrier reefs descend into the lagoon, whereas the reef flat of fringing reefs ends at the shoreline. One thing to take note of is that different areas have different environmental conditions, and because of this, it supports a different type of coral reef species.
Now we start talking about the deep sea sediment, which is really the continental slope and rise. The deep sea sedimentation has two main sources of sediment. One, which is external, coming from outside into the deep water. And the other one is the biogenic, which is forming right there in the ocean. So the main processes which are affecting the sedimentation on the slopes is the mass wasting, which is like submarine landslides, the turbidity currents, pelagic sedimentation, and as I just said, the biogenic sedimentation, especially if we are in the tropical regions. So let's start with the continental slope. The continental slope is often site of turbidity currents. These are bottom flows heavily laden with fine, coarse, suspended sediment derived from the coast and the continental shelf. The currents move rapidly. See, it's coming from probably even from the land. The rivers bringing it through the delta into the continental shelf, and it carves a canyon as it comes down. Then it's going to settle on the continental rise and the abyssal plain. So this is the rise, which is always the site where the turbidity current resolve the sediment settle down. Characteristic of turbidite, as I just told you, it's a grading bedding, which is poorly sorted sand and granules at the bottom of the beds and very fine grained mud on the top. It's usually cyclical deposition, and they are relatively thin beds. See, every one of these, it's a different turbidity current. And there will not be any kind of cross bedding because this is just not the place where that happens. We are at the abyssal plain sedimentation. We have to talk about two different kind of sediments. One is the terrigenous one, which is derived from the continent, and they are transported by rivers, wind, ocean currents. The second one is the biogenous sediment, which originate from marine organisms. We have two kinds, the calcareous, which form from shells of organisms like foraminifera, meaning that the skeletons of these creatures have calcium carbonate. The other one is the siliceous ores, which is from creatures which have siliciclastic skeleton, SiO2 basically. And it's like diatoms or radiolaria. And then we have the hydrogenous sediments, which are forming from direct precipitation of the seawater. What is really interesting that the accumulation rate in this environment is extremely slow. It's about 1 centimeter every 1,000 years. So it's very, very low. And then the last thing we have to talk about is the trench sedimentation. The trench sediments can range from coarse sand and gravels near the trench walls to finer silt muds on the trench floor. The composition of the trench sediment can vary significantly depending on the local geology and the sediment sources. The last thing I want to talk about is the CCD, or the carbonate compensation depth. Carbonate compensation depth is the depth below which calcium carbonate will not precipitate. Above it, you will have limestone forming possibility, especially in the tropical areas, but below it, definitely not. That's when you have either clay or SiO2 material, which can form from the diatoms or radiolaria. I hope you enjoyed this module, and I definitely will see you in the next module, and I see you there.